Tim, I apologize for that, Kuniski, and Florence Zakala. Now, you might have an impression from the program description that this is heavy NYU representation, because Afonso and Tim are from NYU, but this is somewhat misleading because we actually have a strong Swiss representation, because Afonso now is in ETH and Florent is in EPFL. So as was mentioned earlier, the open problem session is canceled, but no despair, because we're gonna instead refer you to an excellent collection of open problems that have been created and discussed during the bootcamp program late August. And we will work around to make sure that everybody who's interested has access to those. So that's my short introduction. We're gonna start in a couple of minutes with Afonso's talk. Afonso is going to experiment with the latest Zoom technology and the latest software technologies he's gonna write on the board. And I've checked that. So suggestion is, I'll repeat what his suggestion is, to pin the video. So pin the video, you're gonna see him in sort of big mugshot, and also the board. And it seems visible. It works for me. Hopefully it works for others as well. But just in case, in parallel, he sent a link to the in the chat that you should be able all to see, where you can also independently link to his slides. As always, feel free to post questions in Q&A, and I'll do my best to relay those to the speaker. Not sure if there is anything else of organizational matter. Afonso, we're gonna start in 1.5 minutes.
Sounds good, thank you.
I don't have ABBA music as prepared. I forgot about it.
I don't either. I don't know if you were asking me, but
no, it was not. You already done. You already done your thing. I didn't do my homework yesterday. Ryan filled this very important gap of few minutes with some nice music from ABBA and other, and I was hoping to do the same, but I forgot.
Afonso, what I like about the presentation software you're using is that with optical character recognition, I can easily and quickly search for phrases anywhere on your slide.
Yeah, it's we'll see how well it works. But yeah, with the right software, you should be able to transform this into any other presentation mode. Transform this. I mean, I feel I haven't watched a board talk in so long that I feel like. I haven't watched a board talk in so long that I feel like.
I did just get a big echo there, though. I'm not sure.
Yeah, it's coming from me. I can mute myself, but I'll have to unmute myself from time to time. So, not sure.
Yeah, but maybe we should make sure that it's not coming from my machine, because is the echo gone? Make sure that it's not coming from my machine, because is the echo gone? Okay, test. Yeah, I think it was David. Yeah. Should I start?
Yeah. So it's.
Should I start?
Yeah. So let's start. I'm gonna mute myself, but I'll unmute myself from time to time to ask related questions. So Afonso Bandeira, our first speaker. Go ahead.
Thanks so much. It's a bit hard for me to see the chat, so please, if you have questions, ask there, and they can relay them. Okay, so hopefully this will work. I'm counting on the fact that you miss board talks as much as I do. We'll see if that's the case or not. And yeah, so this should work fine. Sometimes Zoom lowers the bandwidth, and I don't have any control over that. So there's also a YouTube stream going in HD that's usually very reliable. So if you go and just change the option for HD there, it should work, and you have the link in the chat. Okay, so today I'll talk, it's a short talk, more of an advertisement about equitable colorings, and in particular, the problem of the computational hardness of refuting coloring and the idea of quiet plantings. Okay, this is joint work with a wonderful set of co-authors, I think all of which are in this call, maybe. So this is joint work with Jess at Berkeley, Chris at Santa Fe, and Tim and Alex at NYU. Okay, and Tim is going to give the next talk, incidentally. Okay, so let me define the object of study, right? So the object will be a deregular graph, right? So uniform and uniformly random deregular graph. Okay, and I'll be interested in understanding the coloring number of such a graph, right? Or what happens with hyperability. And so a coloring, or a vertex coloring, right, will be an assignment of colors. To each vertex you assign a color. That's a K option. So coloring assigns K. Right, it will be a choice such that, right, if node I is connected to node J, or belongs to the edges of the graph, and it must be that they're colored with different colors. Okay, this is the idea of just a definition of a vertex coloring from graph theory. And now the coloring number, the chromatic number of a graph is just the smallest possible. Smallest possible K. So, of course, I can always color, within colors, I can always color the graph very easily. Just each node gets a different color, I should say, on the vertices. I want to do something a little more interesting, and I want to get as few colors as possible. And we know that the chromatic number is roughly something like d over 2 log. And so you might now ask the question, right? If you're trying to understand the computational hardness of this problem of coloring the deregular graph, you might ask the question of, okay, so what about if I actually want to be able to color the vertices in polynomial time or efficiently, and then we don't actually know how to do it with less than double the number of colors, right? So if we have around d over log d colors, it's rather easy to do it, but we don't know how to do it with less. But the question here that I'm interested in is a different one. I'm interested in the problem of understanding when is it that I can refute the existence of a color, right? So for which value of k can I refute that there exists a coloring of size k, right? So I'm given a graph that was run at random, and I want to produce a proof that there is no coloring of, right, that there is no coloring of size k, right? So I want to give a lower bound on the chromatic number. Okay, so let me erase. This erasing software is a little slow.
Hey, how did you do that beautiful slide transition? Is that a new Keynote feature?
Well, the problem is that you have to do it in all of them. It's a good 30 seconds in the end. Yeah, someone should implement this on Beamer. Okay. All right, so okay, so the question is, for which k refute efficiently right. What I mean by another way is efficient algorithm. I want an efficient algorithm, right, that shows that proves that the chromatic number is bigger than k. Okay, so what could such a proof look like? Well, for example, the algorithm could just exhibit a click, a k plus 1 size click. Right? If an algorithm can exhibit a k+1 size clique, then this is certainly a proof that you cannot color with k colors, because in particular you would find an issue here, right? But algorithms don't need to necessarily be of this type. Right, but you can just imagine some algorithm that will give Lorgan, right? Think some square spectral algorithms and so on. Okay, so the algorithm that, the simplest algorithm, of course, the simplest algorithm is to just exhibit a clique, but at the size of colorings that we are, it's not clear that we can do this efficiently, or even that this is a good idea that will provide a good bound. But one easy Lorgan on the chromatic number is just obtained by a spectral bound. Right, just what's called Hoffman bound. Right, the idea being that coloring, or these results in coloring are better described in terms of cuts. Right, a coloring is just a particularly big K cut. Right, and so let me define the maximum K cut of the graph. This will be at the fraction of edges that we get cut by the choice of this partition, right? So you can think of this as a color. So I'll do it. And get cut. Okay. So if sigma is a candidate coloring, this is just a fraction of bichromatic edge. And so in particular, written this way, the chromatic number is simply the smallest value k for which I can get this to be 1, right? Because in the coloring, every edge better be bichromatic. And so this is just the minimum among k such that I'm saying G is 1. Right? Why am I getting here? Because
Afonso?
Yeah.
It seems like lots of people are still having issues with seeing you only as one of the Zoom videos, and so we're trying to resolve it. So could you? I will promise to give you back your time.
Okay.
So,
yeah. No, it's fine. Can you just give the stream link?
We did several times. So you can
Someone asked to spotlight the video, but I'm not able to do this. I think a host needs
I'm monitoring the stream, and it looks like it's been resolved.
Who is that?
This is Omid from Simons.
Okay, thank you. So it's all resolved?
Yes.
Okay, thank you. Thank you so much. Okay.
Wait, I didn't understand. Is the stream working or no?
Yes. Yes.
Yeah.
Excellent. Okay, thank you. Sorry about that.
Sorry, but is it? Maybe I don't know where I can change on this side.
Go ahead. Go ahead. We're good.
All right. Okay. 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 So the point being that upper bounds on the maximum K cut give lower bounds on the chromatic number, right? So really the goal is upper bounds. An upper bound on the maximum K cut will effectively give a lower bound on the chromatic number. If I can upper bound maximum K cut away from 1, I know that there is no color. Okay? Okay, so now it's kind of clear what to do, right? We just upper bound the maximum K cut by a spectral bound, right? This is known as Hoffman's bound. Okay, so of course I don't have time to prove this, but the proof is simple and very nice. Okay, this is from I think 1970. Okay, and it says that for a deregular graph, maximum k cut of G for a deregular graph is smaller or equal than k minus 1 over k, and 1 minus. I'm writing the things like this for a reason. Over D. Okay, so written this way is kind of clear what this bound is saying, because if I was to just pick a random k cut, right, the number of edges that get cut is k minus 1 over k. So this contribution just comes from a random k cut. Right? Let's try to pick cleverly the choice of the partition, right? And this is how well, this is the deviation from the random cut, right? Where A is the adjacency matrix of the graph, and of course the minimum eigenvalue of the adjacency matrix is a negative number, right? One way to see this is that the trace is 0, so there must be both positive and negative eigenvalues. Right, so this is an upper bound that one can do, and it's completely efficient. Given the graph, you can definitely compute the minimum eigenvalue of the adjacency matrix, and you know for sure that this is an upper bound on the maximum cut. And so if this upper bound is away from 1, you know that you cannot possibly color with k, and you can now work out what this would give you, which k this would give you, right? Which I won't do today. Now the next question is we're interested in understanding what this does for random deregular graphs, right? So for random deregular graphs, we just have to go see what is the typical value for the minimum eigenvalue of it, right? This is the treatment from 2003. We know that the minimum eigenvalue of a regular graph, random regular graph, deregular graph, is around -2, with lower terms depending on n, which I'll not. Right, so this means in particular that we get an upper bound for a deregular graph. The upper bound, the typical value for the upper bound is -1 over k times 1 plus 2. Okay, so this gives us the typical effectiveness of the spectral upper bound for a deregular graph. And in particular, now we can ask, what does it do for coloring? Right. What does it do for coloring? And for coloring, it roughly gives, I mean, I'm being not super careful because of time, but it will roughly give you something like d over 2 with lower order terms in the lower order than square root of t. Okay, so what this means, I lost the thing. Okay, so what this means is that we get a lower bound of the chromatic number, right? If we apply the spectral algorithm, the spectral bound, we get a lower bound of the chromatic number of square root d over 2, right? This is very different from d over 2 log b. And so what I want to do in this talk, very briefly, is to describe evidence that we have that actually this is unimprovable. And so I'll do this in my remaining 10 minutes.
Hey, Afonso, quick thing. There's a typo in the Hoffman bound that some people are pointing out. You have like a double negative there. Like you should have +1 plus that expression. That's
yeah, there's that, right. You're right, thank you. Yes, I did a triple negative rather than a double negative, right? There's the negative from here. Yes, you're absolutely right. Thank you. Okay, so how do we argue that, right? Conceptually, how do we argue that this is unimprovable? How is our evidence formulated? It's formulated in the way of what we call a computational quarantine. Okay, the idea being of having a distribution over deregular graphs for which the chromatic number is actually a lot smaller, but which we believe that distinguishing this distribution from a deregular graph, from a uniform distribution over deregular graphs, is difficult. And therefore, if we had an algorithm that could give a better lower bound on the chromatic number efficiently, it would work with high probability in uniform deregular graphs, but it would have to fail in this other quietly planted distribution because it's not true, the bound is not true there, and so therefore it would be a way of distinguishing, right? But we believe that it is hard to distinguish these two distributions, right? So this is the key idea, right? This idea has been used in other problems before, right? So what is the trivial way of trying to plant? Right? The sort of trivial, or I should say maybe naive planting. And it's best to think about these things in terms of cuts, right? Rather than coloring. We're trying to plant a large K cut. Right? And the most trivial way to plant is you pick an assignment. Right? So you pick some assignment, sigma, the possible coloring, and you pick sort of the strength of your planting, which will be determined by parameter lambda, eta. And now you just draw a random graph, which we call the stochastic plot model with indices. I guess I need an N, a D, a K, and an eta, right? Which is a random deregular graph condition on this choice of cut, this choice of partitioning having a large cut, right? So let me just write the proper equations. The edges cut by sigma over the total number of edges. I want it to be bigger or equal than k minus 1. Okay, 1 minus k. Okay, so here I'm doing things in sort of a strange way. This is for historical reasons when dealing with the stochastic loss model, that we think of eta positive as having more connections within communities than across communities. And so really we say that should be negative here. Right, and so just to draw a little picture that will help. Eta is basically can live between 0 and minus 1 over k minus 1. And here you do no planting. Right, so here this is just a normal, a uniform deregular graphs, and here you're planting a color. So this is the most naive way of trying to plant a large K cut, and you can see, right? Because of time, I won't show you the calculations for this, but you can see that as I decrease eta, as I make eta closer and closer to here, then I will have larger and larger cuts. Potentially, the graphs produced by this planted model will look more and more different from just uniform deregular graphs. And all the question one has to ask ourselves is, for what values of eta and k do I believe that it's actually difficult to distinguish between these two distributions, right? So let me write that. Okay, so these two distributions are conjecture. Right? This is often known as the SVM conjecture. Right? Is that distinguishing just the normal uniform deregular graphs over n vertices and this new distribution that has now a larger k cut, and d k. Let me see if I get that. Right, it's hard. Right? Making just the hypothesis testing between this is hard if d is smaller than something which is referred to as the Kestenstegen threshold. Okay, so now this means that I can go all the way just shy of the place while it's still hard to distinguish, but they're as different as possible. And whatever cut I get there, I shouldn't be able to work around any better than that. Right, and now I can go see what is the value of this cut, right? And in particular, it tells me that I shouldn't be able to upper bound cuts better than okay. Now I don't have it, and going back to the previous slide is a little hard. But if you know, now the important thing is that if you go look at what is the limit that it shows on the upper bound of maximum K cut, right? There's a factor of 2 missing here. Right? In particular, what it says about chromatic number is that it should be difficult. That it should be difficult to lower bound the chromatic number anything better than square root of d. Right? But so the lower bound we have is at square root d over 2. Right? And this construction tells me that I shouldn't expect to do any better than square root d. Right? But there's still a gap of 2. So the point here is that, you know, at least in this planting, it seems to be leaking information somehow, right? Because, you know, I have my deregular graph. I'm saying that we believe it's hard to give a lower bound on coloring or an upper bound on the chromatic number better than square root d over 2. But when I try to create, at least in the trivial planting, right, I'm shy by a factor of 2. I'm off by a factor of 2, and it begs the question of, is there anything in between, you know, square root of d and square root of d over 2, where there is a better upper bound, not given by the spectral method, but maybe something like sum of squares, right? So we know, for example, that sum of squares degree 2 doesn't improve, right? It also stops at square root of d over 2. But now the question is, can we do a better planting? Can we do a planting of a graph that has now bigger K cuts, right? Whose chromatic number goes all the way to root d over 2, right? Assumes the coloring with a lot less colors, but for which we still believe that it's quiet in the sense that it's still difficult to distinguish from a deregular graph. Okay? So now in my 2 minutes, let me describe what the idea is behind this, and then I'll show you just the construction, right? So this is maybe more for the experts, but what appears to be happening here when we do this kind of planting is the same thing that happens with the spiked random matrix models and the push-out phenomena. So if you have, like for those of you that are familiar with these things, if you have a random matrix and you add a rank 1 perturbation to it, oftentimes the rank 1 perturbation doesn't need to be as high as the right, doesn't need to be higher than the spectral norm of the noise, and still one eigenvalue pops out of the support. This is known as this pop-out phenomena in the so-called BBP transition in random matrix theory and spike models. Okay. So what appears to be happening is exactly this. Maybe another way to think of this is that somehow the noise, the randomness in the model, together with the planted cut, is creating an even bigger cut. We don't actually know if it's creating an even bigger cut or not, but it's creating at least an even bigger eigenvalue or an even smaller negative eigenvalue. Right? So the problem here is that the randomness in the model, you can view this as noise, and the signal, which is the actual coloring that you're planting, right? The cut you're planting, they are not fully orthogonal, and so they're creating something even stronger. Right? At least in the spectral sense, and this has been understood, well understood in random matrix theory. And so the idea is to remove this. In random matrix theory, what you can do, you know, in matrix problems, oftentimes you can do a planting by, instead of adding something, which is very much this type of conditioning, you can just rotate the spectrum. Of course, you know, if you have a deregular graph and you're trying to rotate the spectrum, this is tricky, right? Because you're not going to get a graph in general. And so what we do instead is we plant an eigenvector. Because if you plant something that's an eigenvector of the matrices we care about, in particular the adjacency matrix, then for sure it will have to be orthogonal to the other ones, and so we won't cooperate with the noise to create a push-out phenomenon. And this is exactly what the equitable model achieves. The equitable model is just a planting of a cut that is an eigenvector of the adjacency matrix. Okay. I don't know, do I have any time to just write the model, or? I mean, the model itself is not
Yeah.
Okay, I would say the idea behind the motivation behind the model is more important, but I can write the model if I have a minute, like the actual planting.
Why don't you go ahead for another 3-4 minutes, because we had technical interruptions, so we're going to take 5 minutes from break.
I have a question.
Okay,
Can you write the model?
Okay, so the idea might seem a bit strange because actually,
I think Ryan had a question.
Sorry, I didn't hear. Go ahead.
It was just, could you write the model, please?
Since I was given time, thank you. So, okay, so the idea is to write what we call the equitable model. I mean, this was sometimes it's also called the regular model. This is not our invention. Okay, so it means again, you pick an assignment, and you pick, of course, the strength of the model. And now to make it an eigenvector, you just make every node have sort of the same neighborhood, right? That's what we mean by equitable, right? And so in particular, I'll just write it. So each node, right, it's connected to D neighbors because it's a D regular graph. We make it be connected to right, neighbors, or connected to the neighbors, let's say. Any community, and to the in each of the other communities. Okay, so and now you just draw, a random deregular graph condition on this, right? You can use, you can do these half edges and then just make some random matching between them. This is not so hard to draw. Okay, so the point is that each node now, right, is not just that, in between each community there's a certain number of edges, but each node gets connected exactly to the same number of vertices to each one of the communities, just a different one to its own community. Right, and again, it's the same thing. If I take eta to be minus 1 over k is what makes this 0, and so you're actually planting a coloring. And if eta is 0, you're not planting, you're still planting something, but you're not planting a cut. Right, and if you think about, it takes maybe a couple of minutes, but if you think about it, you can see that this is an eigenvector. If you think in terms of some kind of diffusion on the graph, it's kind of clear, at least intuitive, that this should be an eigenvector. And the point is that this is much quieter. So this is at least spectrally quiet, in the sense that it doesn't create this push-out phenomena. Okay, and in particular, it goes all the way to the right cut and to the, you can go all the way to planting colorings of size squared t over 2. Right, and so it is evidence, gives evidence Hoffman is optimal. Okay, now I just want to say, and even for, if you want to say have k equals 2, it does suggest a way of quietly planting max cut on a deregular graph that goes all the way to the spectral threshold. Okay, so just 30 seconds to give now the issues with this. Right? Of course, this is not really quiet in the right sense of computation because it is an eigenvector. So you can just compute the eigenvectors and you see a suspicious looking one. Right? So you need some kind of noise operator. So you need to have this model and then shake it a little so that the algebraic structure goes away. Right? A bit similar with the issues with XOR SAT and so on. We're not quite sure what the right noise operator is. In particular, we're not quite sure if we're allowed to do a noise operator that keeps the coloring, or you can just say something about near colorings. The other issue is that these numbers need to be integers. Right? Otherwise, it's hard to define the model. when D is large, this is not a problem at all. And in particular in coloring, because 0 is already an integer, this is also not a big issue. But if you want to say do k equals 2 max cut and d equals 3, this is disastrous. Right? So for small values of d, this, in fact, yeah, the cut you plant for 3 regular graph, 2 cut, just max cut, the cut you plant is actually smaller than the largest cut that's already there by randomness. It's that bad. Okay, so I think the two natural follow-up questions are, one, what is the right noise operator, and how can we even argue what is the right noise operator in general in when this kind of extra algebraic structure appears that cannot be seen by things like belief propagation and spectral methods. And two, how do we deal with small d? And I should say, of course, this is the technical contribution of the work is, of course, that we give evidence that this is actually quiet all the way to that via sort of a multitude of methods. So BP analysis, like traditional Kasten-Stegen, the local statistics STP that Jess and Sinan talked about yesterday, and a low-degree method type evidence. Okay, sorry for taking a few extra minutes, but giving only the positive side without the drawbacks wouldn't be so fair. So I'm happy to take questions.
Can I ask a question?
Yeah.
Well, just kind of answered one question, which I guess is like another way to do it is like you take like some kind of like barbell graph and make like a random lift of it. This is your model, maybe in the case of k equals 2, but did I understand correctly that like if you take literally what you have on the board right now, it's like not actually quiet in the sense that there is an algorithm that distinguishes?
Yes, because what you're planting is actually an eigenvector.
Right. So then what is the model? Do you have like a model that you actually conjecture is hard, computationally hard?
Yeah, so we just randomly flip a few of the edges.
So what does it mean exactly?
So you take take a small enough epsilon and now randomly swap epsilon fraction of the edges, and you can take this epsilon as small as we want to believe, if you let the other thing n go to infinity afterward. But so I would also put out a limb and say that maybe even if you do that condition on keeping the coloring, this should still be okay. But it starts being a bit fishy if you start having this noise operator depending on the planted structure.
Oh, right. So you're saying it's not actually colorable anymore in this case?
In this model, no. All you can refute is existence of near colorings.
But to be like very picky, like, do you have a model that for coloring that you conjecture is computationally hard?
Yeah, so I don't know if my co-authors would be willing to be quoted on this, but I would say if you just flip edges at random but condition on keeping the coloring, I would be surprised if there's an algorithm that can pick this up. But I also don't know how to argue this, right? Because in XOR stat and so on, there's the same issue where it's not clear how to argue that. Right? But what we do show, right, the things like the local statistics STP, BP type analysis, low degree, and so on, they don't see that this is an eigenvector, right? So that we show that method is, for those methods, this is quiet, but of course it's not really quiet, right? Just like XOR stat.
Right.
And those methods don't see, if you flip a few of the edges, they don't care, or they care only slightly.
Right.
Yeah, if I can comment on this, I mean, in this middle zone, this Gaussian elimination algorithm is finding this eigenvector, but it's in the so-called bulk, right? It's in the bulk of the spectrum.
Right.
So there are lots of other eigenvalues very close to it. So I guess the intuition is that even breaking that a little bit would confuse it with other nearby eigenvalues and have it really get lost. But it's not clear how to approach that rigorously.
Right.
Other questions, comments? Sihan, you want to ask your questions live?
Sure. Yeah, so I was wondering whether you have any insight on if there's an a planar distribution against an Erdős-Renyi style graph. And the reason I ask is because somehow if you want to construct SOS lower bounds using planar distributions via pseudo-calibration, it's good if your null distribution is product.
Yeah, so I don't know how to do this for Erdős-Renyi. Maybe some of the others have more insightful comment. Yeah, it's not quite clear how to do this.
Yeah, I guess lifts is like very special to regular graphs.
Right, because the planar structure is such, right, is so structured that, yeah, it's not completely obvious. But maybe by attempting to do something like this for an Erdős-Renyi graph, we might even learn how to make the planting less quiet. I'm not sure.
Mm-hmm.
But maybe for that question, like the motivating principle should be this idea of planting an exact eigenvector. So I think in principle, you could try to write down what condition you would need on your planted structure to make it an exact eigenvector, and that would motivate maybe what to do. But yeah, we haven't really looked at this.
Although, sorry, in the Erdős-Renyi case, you don't want it to be an eigenvector of the adjacency matrix. You would want it to give you an eigenvector or a mirror eigenvector of the non-backtracking matrix. So that's the thing whose spectrum is kind of controlling the KS threshold.
Yes, that's a good point. Okay, so it's a bit more complicated than what I said, yeah.
And it's hard to see how to do that with a discrete structure like colorings, as opposed to some kind of weighted structure that compensates for the variance in the degrees.
Yeah, that makes sense. It's a pretty tricky question.
Even for max cut, right? It's not clear how to do this for just for k equals 2. How to do this for Erdős-Renyi, and these kind of SDP lower bounds negative results go through this kind of more abstract like interpolation mechanism. You know, you don't really build an explicit point. So it's, yeah, I think it's not clear how this spectral.
I mean, there is in a way like the completely other side of this, which is the sort of Gaussian analog of these. And this we can give, you can define Gaussian analogs of these objects. So the k equals 2 would be the Sherton-Kirkpatrick Hamiltonian. And this is actually in part what motivated us. And there things work, but in Gaussian models, you can just rotate the spectrum. So you don't have to worry very much, right? You just change the spectrum at will, and yeah, the distribution doesn't really change.
Wait, the point about rotating the spectrum is that you don't have this issue that it's not really quiet?
So in the SK, right? So in the SK problem, what that would correspond to is having having a Wigner matrix and certifying an upper bound on the quadratic form over the hypercube. Right, and so the value of this is like 1.5, but we believe you can't certify any better than 2. Right there, you can come up with a random model. I mean, you can come up, I guess, with 2 random models, right? One would be that you make an eigenvector and then draw the Gaussian matrix completely orthogonal to that eigenvector. But another random model that doesn't have these kinds of issues is where you just grab the Gaussian matrix and rotate its eigenvector so that there is an hypercube point on the top of the spectrum. Right, because if you rotate the spectrum, you can condition on the value of the eigenvalues and rotate the spectrum at will, and because it's rotation invariant, the Wigner matrix, this is okay.
Afonso, it's time already for the floor.
Okay, yeah, sorry. I'm happy to chat offline, of course.
Let's thank this speaker.
Thank you.
And thank you. And Tim, you're on.
Yes. Okay.